Today's lecture, we're going to start talking about bivariate random variables. So we're doubling the amount of random variables, we're doubling the fun. So here we're going to be talking about multiple random variables at a time. So if I had x, that's a random variable, which means it's a function from some sample space to the real line, and I have another random variable y, also a function from the sample space to the real line, then I could consider the pair x comma y, and we'd call that, we'd say that x comma y is a bivariate random variable. So it's basically pairs of univariate random variables. And so the picture that you could kind of have in your head here is that, for example, we might say we want to calculate the probability that my pair, my bivariate random variable, x comma y, is in some set, and let's call the set C. So here, now, whereas in the univariate case, that we talked to up to this point in the class, where we had the random variable was kind of a one-dimensional univariate random variable, now C is going to be a subset of the plane. We're dealing with bivariate random variables. So the picture you might have in your head is we have this plane here, which is R2, and we have some set in there, which is C, and my random variable, you can think of x comma y instead maybe as some random variable z, and this would be, instead of a function from s to the real line, this would be a function from s to the plane. And so if I ask, for example, what's the probability that x comma y, or maybe z, was in some set C, what you could have in the back of your head is that the way we would calculate that is we would look at the inverse image of C under my random variable z. So here would be my set z inverse of C, and you could ask about the probability of this set in my sample space. So the probability of x comma y being in C, where C is some two-dimensional set, or some subset of the real plane, this would be the same thing as asking kind of formally about the probability of the inverse image of Z under C. So that kind of is the theoretical foundations there, where this, again, we'll just map back to our sample space, and that kind of probability, if you think way back to the beginning of class, that's the probability of an event, and we kind of know how to deal with that kind of event. So it's all kind of theoretically grounded, and we're basically just dealing with pairs of random variables now. Often, we'll deal with a set C that is kind of the Cartesian product of two sets A and B, where A and B are subsets of the real line. So C, which is that Cartesian product, would be subsets of a subset of R2. And so we might say, for example, what's the probability that x comma y is in maybe the Cartesian product AB. That's kind of a weird way to write it. What we would write, so kind of the kind of informalism we would write is we would say probability of that x is in A and y is in B. So this comma here, you'll see these commas all over the place. This is read as and. And so this is kind of, maybe I should put my arrow over here. This is kind of the way we would write it. We'd say, you'll see this often. What's the probability that x is in A and y is in B, where A and B are subsets of the real line? What that really, I mean, you could formally kind of trace this all the way back properly by saying what the probability of the pair is in the Cartesian product. And of course, formally this would mean you could write this as the probability of the intersection of the inverse image of A intersect the inverse image of A under X intersect the inverse image of B under Y, right? So that's kind of an intersection here. And again, that's kind of formally correct. So the picture to go along with this would be that here is my real plane, and I have some subset B and some subset A, and the Cartesian product of A and B would be this square here, right? So that's kind of what a Cartesian product looks like. This will come up later in kind of when we talk about independence of random variables, so I'm going to point it out now. But in the special case where our subset, which I call generically C, is a Cartesian product, typically we'll kind of denote it with this simple notation, just the probability X is in A, Y, and Y is in B. And we'll see that kind of these Cartesian product sets can be useful for thinking about things. In many other cases, it's easier not to think of these as random variables, but or kind of as functions, but think of them just as pairs of random variables. And so that's the way that we're going to proceed for the rest of the lecture. So let's look at an example here. What's an example? Let's say I flip a coin 3 times, right? And there are different random variables we could define for this, right? So one random variable we could define is maybe I say X is the random variable that takes on a 0 if the last flip, that's the third flip, is a tails, and it's going to take on 1 if this last flip is a heads. It's a random variable I could define. Maybe it's interesting, maybe it's not. For sake of example, we're going to consider another random variable. Maybe I could consider the random variable Y, which is just something we're more familiar with. Maybe it's the number of heads among the 3 flips. Okay. And just as an example, I could define my bivariate random variable Z, which would be the pair X comma Y. And I could even write a little table for this. I could have my outcomes, little f's in my sample space. So what are my outcomes? Heads, heads, heads. Well, let's enumerate all these, right? Heads, tails. There should be 8 of them, right? Okay, I think those are my 8 outcomes. And then I could look at Z of S, which is my bivariate random variable, which is now, instead of being just a number, it's a pair of numbers. So in this case, remember, X is 0 if the last flip is tails, 1 if it's heads, and Y is just the count number of heads. So for the first one, the count of number of heads is 3, so Y is 3, and the last one is a heads, so I have a 1. In my second one, heads, heads, tails, the last one is a tails, so I have a 0, and there are 2 heads, so I get 0, 2. And you can go through and fill out what this would be. And we can just kind of quickly write these in, but you could verify them for yourself. Should be something like this. There you go. That would be my random variable. And this, so it's a table. This is what we'd call a bivariate discrete random variable in this case. And it looks kind of like the univariate case, but now we've got 2 variables going at once. And so for the rest of the lecture, we're going to kind of explore some of the topics that we've explored previously, but we're now going to talk about them in the context of bivariate random variables. So we're going to kind of generalize some of the things we've talked about previously in the context of 2 variables at the same time. And later in the course, we'll go to multiple random variables. But we're going to start with 2, so you get the idea. So the first kind of concept that we had done with univariate random variables was CDFs. And we can define a similar kind of concept for bivariate random variables. And we could call it the bivariate CDF of a pair of random variables. 2-dimensional random variable is another way of saying it. And the bivariate CDF, let's say BIV, bivariate CDF, is a function f, again we're going to use capital F, takes in two real numbers and spits out another real number. So in the univariate case, this is just a real valued function, but now we're going from the plane. And the bivariate CDF is defined so that f of little x little y, let's say, so for if we have two numbers, x and y, f, capital F of xy, the bivariate CDF, plugging in xy, is going to be, and I bet you can guess, it's going to be the probability that x is less than or equal to little x and y is less than or equal to little y. And so again, this comma here is my shorthand way of writing and we kind of defined that back at the beginning. We had said that if I write x as an A and y as in B, what I really mean is kind of this Cartesian kind of product form. The probability that xy is in that square. So we could visualize this, right? Now we have to work in the plane, but I have an x-axis and a y-axis. Oh, let me use different notation here. Let's say x-axis and y-axis, and I'll have a point somewhere around here. Well, that's not where it is. Let's try that again. Somewhere around here, x comma y, and my bivariate CDF is going to look at the probability. I'm kind of to the left and below this point, x comma y. So it's a probability I'm in that area. And so it is kind of a very natural generalization of the univariate CDF idea. We can write down some kind of familiar properties, and I'm going to write these down without too many proofs. Some of these will be familiar, and some of them are going to be new. So first of all, the bivariate. So let's say this is about bivariate CDFs. So let's say bivariate CDF properties. Okay. First property is that the bivariate CDF is bigger than 0, right? Proof of that is basically it's a probability that it would be bigger than 0. Some other properties. In the univariate case, we had some limiting properties. In the bivariate case, if we look at the limit as both x and y go to infinity, we're going to get 1. So in the univariate case, the analogy was that if we looked at the limit as x goes to infinity of that univariate CDF, that gave us 1. And similarly in the bivariate case, if we send both variables to infinity, we get 1. Third property, if I send either of my two variables, x or y, to negative infinity, I'm going to get 0. So if I send x to negative infinity of fxy, fixing y, I'll get 0. Or if I fix x and send y to negative infinity, I'll also get 0. And this is kind of the analogous case where in the univariate case, I had the limit at negative infinity of my univariate CDF was also 0. And let's say the fourth property, which is very analogous, is that f is non-decreasing. And let's just combine things and write continuous in each argument. And you probably believe that, and you can look at the proof of that for the univariate case, and you can think about how you might prove it for the bivariate case. But this is analogous very directly to the univariate case, where the univariate CDF was non-decreasing and right continuous. And in this case now, we just to say it's true. If I fix one of the arguments and change the other one, it'll be non-decreasing and right continuous in either of the arguments. So nothing too amazing or groundbreaking there, but some, just a nice feeling that these same facts that were true in the univariate case also generalize to the bivariate case here. Okay. So we can define the bivariate CDF. We should talk real quickly about what a marginal distribution is. So the bivariate CDF is going to kind of characterize the bivariate distribution. The marginal distributions are just the kind of distributions of either of the arguments or either of the random variables. So if x comma y is a bivariate random variable, then basically we say x and y are the marginal random variables, and their distributions kind of respectively are called the marginal distributions. And we'll see where that word marginal comes from. But it's just a way of talking about the kind of component-wise distribution of the kind of bivariate random variable. So I introduced the marginal distributions because we can now relate this bivariate CDF to the marginal CDFs, right? So the random variables x and y individually are just univariate random variables. They have all the same things any univariate random variable has, a CDF, PDF, or PMF in this case. Moment generating functions, all those kind of great things. And there are some relationships between the bivariate, say CDF, and the univariate CDF. So let's write that theorem down. Let's say relation between bivariate and univariate CDFs. So this kind of fact or theorem has two parts. One, the marginal CDF of y, which I'll write as Fy of y, can be attained from the bivariate CDF as the limit as x goes to infinity of the bivariate CDF. So if I fix y and send x to infinity, in the limit, that's going to give me back my univariate CDF for y. Similarly, if I want the univariate CDF for x, I can fix x, send y to infinity, and if I do that for my bivariate CDF, I will get the univariate CDF for x. So these are the univariate CDFs, and F here are the bivariate CDFs. And we can make the kind of argument, I won't call it a full proof, but let's write proof. The idea, maybe we'll just be more general and say idea, not really a formal proof, is that, for example, if I want the marginal CDF of x, the marginal CDF of x is the probability that x is less than or equal to little x, which we could write as the probability that x is less than or equal to little x and y is equal to anything. Right? So that's okay, right? Kind of tacking on y being anything is like this, event with probability 1. It doesn't really change our probability. It's the probability x is less than or equal to x and y is anything, right? Okay. And we could write that as the probability x is less than little x and y is less than or equal to infinity, let's say. Maybe we'll just say, well, let's just leave it as less than or equal to. It's a little bit of abusive notation, but this is not kind of a formal proof, just kind of an idea of what's going on, right? So you could say that the probability x is less than or equal to little x is the probability x is less than or equal to little x, and y is whatever it wants to be. Because the probability that y is anything is just 1. So I'm just kind of intersecting this with the probability of 1, in fact. Or the probability that y is finite. And so in the limit, this is kind of the limit, the more formal way to write this, as y goes to infinity of x is less than or equal to little x and y is less than or equal to little y. But of course that is just the definition of my bivariate CDF. So not kind of the most formal proof in the world, but the kind of general idea of how you would actually show it that way, which is that I can basically send y to infinity, and it kind of gets rid of that effect. And I'm just left with the CDF of x. So that's a useful fact to know, is to know that if I look at the limit at infinity of x, I get the CDF of y, or y, I get the CDF of x. Okay. So what are some other theorems about the CDFs? So let's call this a lemma. A lemma is just kind of a short, simple little theorem. And our motivation here is that for univariate, we have the fact that if I want to calculate the probability that x is bigger than some value little x, that is 1 minus the CDF of x. And for bivariate, it is the case that if I want to calculate the probability that x is bigger than some little x and y is bigger than some little y, I can play a similar game. It's a little bit more complicated than the formula. It is 1 minus the CDF of x, the marginal CDF of x, minus the marginal CDF of y, plus the bivariate CDF. So I'll put this in the box. This is kind of the important theorem. This looks kind of familiar. It looks like what? It looks like one of the basic theorems we had, which is that the probability of A union B is the probability of A plus the probability of B minus the intersection AB, right? And indeed, basically, that is how you would prove it. Like you would directly prove it that way. And you can, for the similar way, you can draw kind of a picture proof of this fact. You can do a similar kind of proof for our theorem relating our little lemma up here, right? So let's draw a picture. I'm going to have my two axes. So this is kind of my x-axis and my y-axis. And I have some point here. Let's call it little x, little y. And I want to calculate the probability that x is bigger than little x and y is bigger than little y. So visually, that is kind of this region, right? So underline that in blue there. That's what I'm going to calculate. It's kind of the area to the right and above this kind of this rectangle, right? So one way I could calculate that is I could kind of subtract off. I could take 1 and subtract off everything but that rectangle, which is effectively what I'm doing here. So I'm going to subtract off two things, but then very similar to my probability of my union, I'm going to overcompensate, so I'll have to go back and adjust at the end. So first of all, what I'll do is I'll subtract off, and let's underline this in red, the probability that the CDF of at x, which we can visualize as basically this half plane to the left of little x. So I can subtract that off, and maybe I'll underline in green the CDF of y, the marginal CDF of y, which would kind of be this half plane below y in kind of green here, right? But now I've kind of double counted this area in black, right? So this kind of black rectangle here, let's say, has been double counted, and so I'm going to add that back in because I've subtracted it twice. So that's basically the theorem. Again, not kind of the most formal super proof, but you could basically prove it with this actually really basic theorem we learned back in, say, lecture 2 or 3. But that would be how you prove it. So some nice simple theorems. There are ways of extending this, but for example, maybe we could write a quick extension. If I wanted to say calculate the probability that x is between some little x1 and little x2 and y is between some little y1 and some little y2, you could imagine extending this. It's kind of an ugly formula, but you could make a similar picture proof to prove it. In this case, it's f of x2, y2 plus f of x1, y1 minus f x1, y2 minus f of x2, y1. And that's basically just going to be subtracting off the right boxes, right? So let's just write proof, similar picture, argument. And you can come up with other theorems for calculating the probability of various kind of rectangles that you want using the joint CDF. Okay. So that's the joint CDF. The other properties that we had looked at for the univariate case was, of course, the PMFs and the PDFs. So let us look at a definition of what we're going to call a joint PMF. So if x and y are both discrete, then the joint PMF, and we'll say parenthetically joint of x and y, is, not surprisingly, it's going to be a two-variable function. We'll use little f to denote it. F of xy, and it's going to be the probability that x is equal to little x and y is equal to little y. So let's put that in our box. This is our joint PMF. And it plays the same role, very much, as the univariate PMF, a one random variable. Now we have two at a time, and so it's the probability x is little x and y is little y. And we can come up with some theorems. A kind of valid joint PMF is that, well, let's say f is a valid joint PMF if and only if, right? So if f is a valid PMF, this will be true, and if this is true, it's going to be a valid PMF. And that's our two facts. It's kind of generalizations. First of all, if I sum over both x and y of f xy, I'll get 1. And 2, f of xy is positive. So that, very analogous to our univariate case. In the univariate case, we said function is a valid PMF if it's positive and it sums to 1 over all possible values in the support. Now we have two variables at a time, so two variable function fxy better be positive. And if I sum over both x and y, I better sum over that plane or that kind of two variable collection to be 1. So that's basically a real quick rundown of the joint PMF. What we didn't have in the univariate case that we now have in the bivariate case is that we have not only the bivariate PMF, or what we're calling the joint PMF, but we also have the marginal PMF. So we have the PMF of X alone and the PMF of Y alone. And there's going to be a relationship. And so we can write this down as a theorem. So let's say relation between joint and, well, let's say joint plus marginal PMFs. So this is where it starts to get kind of interesting. And there's kind of two things we can write. So one, the marginal PMF of X, that is, if we were just to take X alone and look at its PMF, we can get that from the joint PMF of X and Y by summing out Y, as it were. So if I sum over all possible values, so this is my lazy notation for sum over all possible values. If I take the joint and I sum over all values, fix X, and I sum over all values of Y, I get the marginal distribution, the marginal PMF of Y. And the analogous fact, not surprisingly, is if I want the marginal of Y, sorry, I said that wrong previously. If I want the marginal of X, I sum over all values of Y. If I want the marginal of Y, I'm just going to sum over all possible values of X, fixing Y. And so there's this kind of fundamental relationship where I can get the marginal if I know the joint. Now, it's a bit harder generally to go the other direction. If I know both the joints, sometimes I can get back the marginal, sometimes not. But certainly if I know the marginal and I can just sum out one of the variables, sorry, if I know the joint, I can sum out one of the variables and I get the marginal for the other. We can, again, kind of make a kind of quick proof of this. And the proof is basically relies on the fact that if I look at the collection of events y is equal to little y over all possible little y, this partitions my real line, or partitions, maybe more specifically, partitions S, my sample space. So I can basically partition my space by looking at all events y is equal to little y over all possible y in my support. And so if I want the marginal of X, which is in the discrete case, this is just the probability X is equal to little x, right, the univariate, I can use my partitioning rule and say that this is the sum over my partition of X is equal to little x and, or maybe we could say intersect, so I'll abuse notation here, intersect with my event y is equal to little y. So this, if we go back to say maybe one of our early lectures, is kind of the partitioning. Right? If I have some partition of my sample space, I can always write the probability of some event as the probability of that event intersect with each of the things in the partition, and I can sum them all up, right? So this is basically the argument, the picture we did there was a picture like this, where A was my event, and then I had some partition of some B sub I, right? B1, B2, B3, right? And that's the same thing we're using here. We just now have a name that the probability, we can, say the probability, this is the probability of, whoops, that should be X is little x, and Y is little y. Now we just have a name for that, right? This is f of x, y. And that is the proof. I mean, you could write some words to make it seem a little more formal, but that's basically the main idea behind the proof, is that I can get my marginal of x by summing out y. And the same proof goes for the marginal of y. Obviously, you can switch the roles of x and y here and get things to work out. Okay. So that's a really nice fundamental relationship. Now let's look at an example of how that works. And this is going to shed some light on the word marginal and why we use that word marginal. So again, we're going to consider the example of flipping 3 coins. And again, x is our random variable that is either 0, 1, 0 if the last flip is a heads, and 0 if the last flip is a tails, and 1 if the last flip is a heads, right? And we had another random variable y, which is just a number of heads in 3 flips. So let's look at some examples of some concepts. First, let's derive out what the joint PDF is for this thing. Okay. So for a bivariate discrete random variable, where I only have a finite number of options for x and y, right? X can be 0, 1, y can be 0, 1, 2, or 3, right? So I can actually draw this out in just a little table. So here's x and y. X can take on either 0 or 1, and y can take on the value 0, 1, 2, or 3. Okay. Let's just extend our table a little here. We're going to need that in a second. So what I'm going to do is I'm going to fill in each of these squares here with my joint PMF. So for example, what is the probability that y is 0 and x is 0? Or what is f of 0, 0? So f of 0, 0 is equal to, well, that's the probability that the last is a tails and the I get 0 heads. So that would be tails, tails, tails. One of my 8 outcomes. F of, in this case, it would be 1, 0. So that's the probability that x is 1, so my last is a heads, and I have no heads. That can't happen. 0. And so I can fill in my table, right? F of 0, 1 would be the probability that the last one is tails, and I have 1 heads. So I can get heads, tails, tails, or tails, heads, tails. That would be 2 eighths. And I can fill these in. I'm not going to go through and tediously go through each case, but you can fill in probabilities. And this is the table you'll get. So what you should be asking yourself at this point, as an aside, there's a theorem we said that 1 fxy is always positive. Well, that seems true. Or always non-negative, let's say. It's 0, 1/8, or 2/8. Okay, that's certainly true. And the second fact is that if I sum over both x and y of fxy, I should get 1. And if you go through and you derive it all, there's 1/8, 2/8, 4/8 plus 4/8, it sums to 1. So both of these facts are true. It's a valid PMF. So I haven't made any mistakes. So this is my joint PMF. And now I want to get the marginal PMFs. So the reason that the PMFs of x alone or y alone are called marginal PMFs is because I can get them by summing up across and putting the answers in the margins or the edges of the table. So, for example, if I want to get the marginal distribution of x, I sum over y fxy. So I fix x, and then I sum over the possible values of y. So for example, if I want f of 0, this is going to be the sum. In our case, y goes 0 to 3 of f of 0 to the y. And you can see that that is just the first summing across this first row. I fix x at 0 and I sum across my values of y. So it's 1/8 plus 2/8 plus 1/8 plus 0. So that should be 1/2, and that is fx of 0. And if I want fx of 1, I go for the second row. I sum across the 1 row, right? And that's 0, 1/8, 2/8, 1/8. And again, that should give me 1/2. So the marginal distribution, of course, of x is written in the margin, hence the name. So this is kind of a very classical way that people originally derived these things, and the terminology is kind of stuck. For discrete random variables, you could write them as tables, and you could derive the marginal distributions in the margins. And if I want the marginal distribution of y, I can play the same game, but now I'm going to sum across columns. So fy, let me pick a different color here. Let's go with black. Fy of 0 is 1/8. Sum across this, 3/8 will be fy of 1, right? Because all I'm doing is I'm saying if I want fy of, let's say, 2, that is the sum over x is 0 and 1 of f of x2. So it's f of 0, 2 plus f of 1, 2, right? That column, summing across this column. Again, 3/8 is fy of 2, and 1/8 is fy of 3. Notice that these two things, this marginal of x and this marginal of y, they're valid PDFs or PMFs, right? In the discrete case, in the univariate case, they sum to 1, they're positive. They sum to 1, they're positive, right? And so that's a nice little example of a marginal, the kind of relationship between the joint PMF and the marginal PMF. So we have this idea of this joint PMF when we have joint discrete things. Of course, the next thing we want to move on to is the joint PDF, right? So let's say joint PDF, joint PDF. And so if x and y are continuous, we call f, which is a function that takes in 2 arguments and spits out a number, we call f the joint PDF if for any subset, let's say, we call this subset C, right? Any subset C of the plane, of the real plane, if I want to calculate the probability that xy is in this subset, all I do is I integrate fxy over that set C. So joint PDFs always have a very dissatisfying definition because they're kind of implicitly defined. Like, so the joint PMF, we say it's a probability of this and this. The joint PDF, we can't talk, right? We have continuous things. We can't talk about the probability something is exactly equal to this or exactly equal to that. But so the way to properly define the joint PDF is that it's the function that when you integrate it over the set, it gives you the probability of being in that set. And this is exactly kind of what we saw in the univariate case. Recall in the univariate case is that if I wanted the probability that x was in A, what I would do is I'd integrate my PDF x over that set A. And that It's very analogous to what's happening here, but now we have two variables, or two random variables, so we have a bivariate PDF. And so you have a double integral, So it's just like moving from single variable calculus to multivariable calculus. So let's look at some facts of this joint PDF. Yeah, so we can call them facts. We could call them theorem. Let's call it facts. What are my facts? First of all, the facts are that if I want the joint CDF of x and y, which of course is the probability that x is less than or equal to little x and y is less than or equal to little y, I can calculate this as a double integral, negative infinity to little x, negative infinity to little y of, let's say, f of u of v du dv. All right, dummy variables u and v don't matter, but right, and so this is the analogous to for the univariate case, right? In the univariate case, we had that the univariate CDF was the integral of negative infinity to x of, I used t in that case, of the univariate PDF. Now we have bivariate things, so double integrals, right? And the next fact is that if I want to get my bivariate PDF, I can just take I can play the reverse game, which is I can take my bivariate CDF and I can now look at the mixed partial. So if I take the partial with respect to x and y in either order, doesn't really matter, then that gives me my joint PDF from my joint CDF. So let's just box this first fact up here. This is an important fact, and let's put a box around this one, another important fact, right? And again, I'm not really going to prove it, but I'm going to just call for the analogy to the univariate case where my univariate PDF was just the derivative of my univariate CDF. And kind of the last not surprising fact is that let's call it fact 3i is that this thing is bigger than or equal to 0, and it's also, if I integrate my joint PDF over the whole plane, I'll get 1. And this is kind of, so maybe we can write this more formally. F is a valid joint PDF if and only if those two facts hold. It's positive and it integrates over the whole plane to 1. All right. Again, in the univariate case, we had that fx was bigger than or equal to 0, and if I integrated fx over the whole real line, I'd get 1. All right. Same thing here, but now we have a bivariate random variable. Okay. None of those two facts are too groundbreaking, but it's worthwhile pointing out that they are true in kind of a more general sense for the bivariate case. What's more interesting is if we had this theorem here of the relationship between the joint and marginal PMFs, and I bet you can come up with a similar theorem for the relationship between the joint and marginal PDFs. And let's just write it down. So relation between joint plus marginal PDFs. And the theorem is that if I want the marginal PDF of x, I can take the joint PDF of xy and, as we say, integrate out y. Or if I want the marginal PDF of y, I can take the joint PDF of xy and nope, and integrate out x. So in the first case here, basically so here's my plane, here's my real plane, and I am fixing x at some value x, and I'm integrating over this plane, over this slice. So I'm integrating over this whole slice here. In the second case, I'm fixing some value little y, and then I'm going to integrate kind of over this horizontal line, over all possible x at that fixed y. Okay. Not too groundbreaking theorem, I won't go through the proof. Basically, you make the same argument as in the discrete case for the continuous case. Instead, I think the most useful thing for the remainder of the lecture is let's just look at some examples. Let's get real familiar, because basically we've now transformed from a Calc 1 class to a Calc 3 class. So let's look at some examples of all these kind of theorems we've talked about. Okay. So I'm going to give you the joint CDF. So here's my joint CDF. This is a doozy. 0 if x is less than or equal to 0, or y is bigger than or equal to 0. And I'm going to draw an accompanying picture here. Okay. So this is 0, 0, x-axis, y-axis here, right? Let's just not draw those for sake of simplicity. I'm going to say here's 1 on the x-axis and here's 1 on the y-axis. Okay. And I'm going to say I'm going to write the value of this thing. Let's actually denote some more boundaries here, like this. I'm going to write the value of this joint CDF in red. So at 0, if x is less than 0, or y is bigger than 0. Is that right? Nope. That would be weird. Y or y. So it's a positive, it's kind of a bivariate positive, right? So it's 0 everywhere out here below either the x or y axis. It's going to take on the value xy if x and y are kind of in the unit square. So that is this part here. That's xy. And if it's going to take on the value x if y is bigger than 1 and x is in the unit interval. So that's this here. And it's going to take on the value y if x is bigger than 1, but y is in this unit interval. So that's there. And it's going to take on the value 1 up there. So I'll write that. Take on the value 1 if x is bigger than 1 and y is bigger than 1. So that's an example of a joint CDF. It's much more complicated than some other things we've seen. But we could ask a question. So this could be a homework or an exam question is, what is the joint PDF? So I'm kind of hinting here this is a continuous function, and it is therefore a kind of bivariate continuous thing. So bivariate continuous random variable, and so it has a joint PDF. And our relationship, if you recall, maybe we'll write this in green, that if I want fxy, I take my mixed partials, dx dy of this CDF. So all I need to do is take the derivative, one with respect to x and one with respect to y. So I'm going to write this now in green here. Certainly in all the places that the CDF is 0, if I take the mixed partials, I'm still going to get back 0. And the place where it's a constant, where it's 1 up there, if I take the mixed partials, I get 0. And also, if I take the place where it's x, if I take the derivative of that with respect to y, I'll get 0. And then x, I'll still get 0. And similarly, y, the mixed partial is 0. The only interesting place is in that unit square, where if I take the derivative with respect to x first, I get y, and I take derivative with respect to y, I get 1. So in the unit square, I get 1. Oops, well, let's write this in green. Hence, simply, our joint PDF is 1 as long as, let's write it this way, x and y are in this unit square, which we can write like that. So basically, this is basically a bivariate uniform over the square, over the unit square. It's basically bivariate uniform. It has a density of 1 in this square and 0 everywhere else. Kind of like the bivariate version of a uniform. We can also ask, what's another question we can ask? So this is question 1. Let's say question 2. Marginals. Can we get the marginal distributions for these? So what's, say, f(x) of x? We could get this as the integral, right? We get the marginal by integrating out, we get the marginal of x by integrating out y. And so that's got a general formula. In this case, is the integral from 0 to 1. The joint PDF is just 1, minus dy. So the marginal is just 1, and this is true as long as x is between 0 and 1. And it's 0 elsewhere. And you can kind of think about why that's true. Just look at the picture. And this is exactly saying that x marginally is uniform between 0 and 1. And similarly, it's not too hard to show that we can play the same game with y, and y is also marginally uniform, 0 to 1, which is maybe not too surprising, right? Jointly, they kind of have this joint uniform over the square, and marginally, they're uniform. So, nice little example. Let's look at something a little bit harder. Look at a more complicated example here. Okay. So, I'm just going to draw the picture. I'm not going to write out the whole piecewise equation because that would take more time than I want. Okay. So 0, 0. Those are the 1 points. And then this is the line y is equal to x. And I'm going to write the joint CDF in red. So it's, again, going to take on kind of 0 below the axes. It's going to take on, oh, let's draw a couple more things here. Let's draw that. It's going to take on the value 1 if either x or y, if x and y are bigger than 1. It's going to take on the value of x minus x log x over y in this triangle here, and it's going to take on the value y over here, and up here it's going to take on the value x minus x log x. I should probably say this is an example. So that is the CDF. It's a valid CDF. You can actually spend some time. It might be useful to go through and show that it satisfies the properties it needs to satisfy. We can get, say, the joint PDF. Again, the joint PDF, I just take the mixed partials with respect to x and y of my CDF. So certainly where it's 0 already, I'm going to get 0. Where it's 1, I'll get 0. where it's y, I'll get 0. And where it just involves x, I'll get 0. Take derivative with respect to y, that's suddenly 0. And the only interesting place is in this kind of triangle here is I'll get 1 over y. So the kind of simpler way of writing this is that fx comma y is 1 over y for whenever we're in this triangle. And this triangle is defined as 0 less than x less than y less than 1 less than or equal to. Doesn't matter, it's continuous. So that is my joint PDF. And you can kind of do the derivatives, but to get those values, all I did was some partial derivatives, right? If it just involves x or y, or neither, it's going to go to 0. And if I take the derivative with respect to x and y here, the only hard thing you need to show is that, let's say, that let's say this, take derivative of x minus x log x over y, right? And you can either do x first or y first. Let's actually reverse this. Let's do y. Which way is first? Maybe that's the correct way, right? So if I take derivative with respect to y, I should just be left with x over y. People believe that. And you can think about why that's true. The negative flips it over, and I have 1. The derivative would be 1 over that, right? And so that should just leave me with 1 over y. Hence, I get what I have. So I could then take this, and I could say, what about the marginals? For example, what if I want to get the marginal of x? Now this is going to be more interesting because our marginals of x and y are not going to be the same because we don't have kind of just a simple uniform distribution. The marginal of x is, I take the joint and I integrate out y. Oh, I'm sorry. I integrate out just y. And in our case, so let's look at what the picture would be. If I fix my value of x, say here, I'm kind of integrating on this line here, right? I'm integrating with respect to y. So I'm integrating, in this case, 1 over y dy, but I have to look at my limits of integration. This is basically a Calc 3 problem. And it looks like I go from the line y is equal to x to 1. So I go from x to 1. And of course, this is log y, evaluated at x and 1, which gives me log of 1 minus log of x, which log of 1 is 0. I'm just left with log x. So that's the marginal of x. And this is, as long as x is in this unit interval, 0 otherwise, right? Because if x is outside that unit interval, I'd be integrating over a bunch of stuff that would be 0. But if it's in that unit interval, it will have a PDF of negative log x. So maybe I should include that in my box here. And I could similarly ask for the marginal of y, and now this function is not symmetric, so we expect to get something different, right? And so now, let's go back up to my picture. Maybe big blue here. I'm going to fix some value of y, and I'm going to integrate kind of over here. So if y is between 0 and 1, let's say for y in the interval 0 to 1, I am going to integrate from 0 to x, or 0 to y, right? And integrating my joint is just 1 over y still, and I'm integrating with respect to x. And this is actually nice and simple. Y can come out, and I just get 1 over y times y, which is 1. And so my PDF is 1 if y is in that unit interval, i.e., in this case, actually, again, y is uniform over that interval. Okay. So let's look at, so that's kind of, 2 examples of the relationship between the joint CDF. And to get the joint PDF, I take partial derivatives. And if I want the marginals, I just have to do some integration problems. It could be easy, like in the first example, or I might have to kind of set up a Calc 3 problem. There are kind of 2 more examples I think would be interesting to do. So let's look at one of them, which is that let xy have, so now we're going to kind of look at a different case where we're not going to give you the CDF, we're going to give you just straight up the PDF. Have a joint PDF of fxy, and it's going to be 6xy squared, and this is going to be for 0 less than x. So that's my notation for saying both x and y are between 0 and 1. So always useful, as in solving Calc 3 problems, is to draw a picture. So here are my bounds, 0 to 1 on both axes, and my joint PDF is 6xy here, okay? And, or 6xy squared. And you got to convince yourself that that integrates to 1, which it should. I'll let you think about that. And what we're going to ask is, I want the probability that x plus y is bigger than or equal to 1. So recall, how do we calculate this? If I want the probability that xy is in some subset of the real line, or sorry, in some now subset of the real plane, I integrate over the set of now my joint, right? So in this case, my set C is the set of x and y such that x plus y is bigger than or equal to 1. And so I'm basically going to integrate over this area. So let's draw that. So this is the line in red here, is the line where x plus y is equal to 1, or x is 1 minus y, or y is 1 minus x, right? You can think of either of those. And I want the set where x plus y is bigger than 1, so that's kind of everything above that line. Now notice that my joint PDF is only non-zero for part of that. It's only going to be non-zero for that kind of triangle. And so really I can just call that set C and integrate over that set. So probability x, what did I want? I want the probability that x plus y is bigger than or equal to 1 is the integral over that set C of fxy dx dy. And now we basically just have a calc problem, right? I've given you a function, fxy, integrate over this area. From here, it is Calc 3. And so we just have to set the problem up correctly. So I'm integrating 6xy squared, right? That's what I wrote. And I'm integrating dx dy. Okay, so if my inner integral with respect to x, then I fix an x. Oh, maybe we should use black here. I fix an x, and I integrate kind of this slice here, right? And so I'm going to go from, use this equation, I'm going to go from 1 minus y to 1. So my inner integral goes from 1 minus y to 1. And my outer one is just y. Oh, I do that. I'm drawing this picture wrong, right? I fix no, that's right? Yeah. Let me draw this right. Should go horizontally. If I fix on my inner integral with respect to x, and oh, I'm sorry, my inner integral with respect to x, right? So I'm integrating these slices. Sorry about that. Let's get this correct, right? I'm integrating these slices. Got to set these calc 3 problems up right. So I'm integrating with respect to x. So I'm integrating on these slices. It goes from, the math is correct, 1 minus y up to 1, right? So it's this way. And then I'm integrating over y on my outer integral, which integrates kind of these horizontal slices. And that goes from y is 0 to y is equal to 1. So my outer integral goes from 0 to 1. Sorry about that. Got to think for a second. But drawing the picture always helps, right? Because then you don't mess this up. So I'm not going to solve this out. I'll say calc 3 problem. And I'll give you the answer. The answer is going to be 90%, 9/10. So the probability in this case that x plus y is bigger than 1, bigger than or equal to 1, is 90%. And that's the problem, right? So that's how you solve it, right? You draw the picture of the PDF, you draw the picture of the area you want to integrate over, and then you solve the calc 3 problem. You integrate the PDF over the area, just in the same way as the univariate problems. Okay, let's look at one more problem. Again, I'm going to kind of set up the problem and leave the calc 3 details for you to do, because it's not worth my time kind of to pretend like I'm teaching you calc 3 again. You all know calc 3. What I want to do is get from the probability problem to calc 3, and then from there you guys can take it home. Okay, so let's say our bivariate random variable xy has a joint PDF of fxy is e to the negative y for 0 less than x less than y. Okay, so you're going to get problems on homework, on exams that start like this. Always draw the picture. So here is going to be my line. It's supposed to be a line. Y is x. And my PDF is kind of defined in this kind of infinite integral, or infinite triangle here, which is, it's e to the negative y over this triangle, right? This is where y is bigger than x, but x is bigger than 0. And I could ask you the same kind of question. So what if this is a different PDF, but I could say, again, what is the probability that x plus y is bigger than or equal to 1? And so again, what I'm going to do is I'm going to say, okay, somewhere here is my number 1. Somewhere over here is the number 1. I'm going to draw the line connecting them. So again, this is the line where x plus y is equal to 1, or y is 1 minus x, or x is 1 minus y, okay? And I want to calculate, my probability is kind of all of the area above this. So that basically is going to be this kind of blue set I'm going to outline here, right? What I'm actually going to have to integrate over is this blue set. That's the place where my PDF is non-zero. My PDF is non-zero above the red line. And my intersects where I'm interested, the area I'm interested in, above the green line. So that gives me this blue region. So you could call this the set C maybe, right? That's the letter I've been using. So basically, to solve this problem, I have to integrate over that set C. And integrate my function, fxy, in this case it's just e to the negative xy. And the way to set this, so this is a Calc 3 problem. It's a little more complicated than the last one. What you can do is you can break it up into two integrals. You could say there's a region C1 and a region C2. This point here is x is 1/2, and you can verify that's true. That's where x plus y is 1 and y is equal to x, 1/2, right? So you could set this up as the integral over C1 of f plus the integral over C2 of f. And so real quick, let's just set up that Calc 3 problem, right? So C1 is kind of this kind of trapezoid. And let's integrate with respect to y first. That goes from, so if I integrate with respect to y, I integrate with these vertical slices. So that would go from this green line, where y is 1 minus x, and it goes off to infinity. And I'm integrating my PDF, e to the negative y. And then I'm going to integrate over my slices in the x direction from here, x equals 0, all the way to here, x is equal to 1/2. And then my second integral, which integrates over the second region over here. Okay, of course my outer integral is going to be the rest of the x's. It goes 1/2 to 1. That's my outer integral. And my inner integral, so of course my function is e to the negative y. My inner integral goes from, again, I'm integrating with respect to y. It goes from this line, which is the line y is equal to x. So it goes from x, and again goes to infinity. Just those infinite kind of vertical slices. So again, I'm gonna leave this to you. It's Calc 3. You know, basically set up the probability content. It's done. Calc 3 is you do some Calc 3, but I'll let you solve this as an exercise, and I get something like that: 2e to the negative 1/2 minus e to the negative 1. That's my answer. You could also verify that that is a positive number between 0 and 1. It's a probability. Okay, but that's, you know, so that's how these problems are going to feel. So we're going to have some practice problems here, and they're going to start feeling a lot like Calc 3 problems. So we kind of move from Calc 1 problems, where you're solving integrals, to now you're going to be moving to Calc 3 problems, where you're solving multiple integrals. So let's do a real quick recap of the lecture. We did a lot. Okay, so we're talking about bivariate random variables. So we have some examples, talked about bivariate CDF, which is the bivariate version, similar kind of properties. Marginal distributions. So marginal random variables are just the individual components, and the marginal distributions are the distributions of those components. And there's some relationships between the bivariate and univariate CDFs, kind of limiting relationships, and some kind of similar theorems. We also had what we call the joint PMF, which plays the same role for bivariate random variables as the univariate PMF. And you can get the marginal PMFs from the joint by summing across one of the variables and fixing the other. We saw some examples, and you can also define a joint PDF, which again, in the bivariate random variables, plays the same role as the marginal PDF. And again, we had some very kind of familiar properties, and maybe the most useful one is that if I want to get the marginal PDF of, say, x or y, I can integrate the joint PDF across the other variable to get it. And so we had some examples. I think you should recommend going back and thinking about these examples. And then we saw some examples of how to just calculate probabilities, right? So in the univariate case, if I wanted to calculate the probability of something, I'd integrate the PDF over the region. And that's true again in the bivariate case, but now we're going to have multiple integrals. So this is kind of a crash course in bivariate random variables. a lot of kind of familiar concepts we've seen now with two variables instead of just one.